like things, but you didn't go to the shop.
A lot of companies just get big.
So I was like,
So I want to make a big project.
So I couldn't get this corner case where like they didn't visit the shop.
It's kind of a low.
So I could get more people that would go visit shops and only have them.
And I don't know, I'm gonna probably count in like California area, Seattle. Here there's not really much. I probably won't go to the sponsorship. They sent response already, so again, I'm good.
All right, let's get started. So, homework 2 solution is posted. So I want to say one thing about homework submission, right? So we do everything on Canvas, and the deadline is a deadline, right? So I don't control the deadline. I set up a time. Once time is up, Canvas shut down the submission site automatically, right? So I want to give a few minutes to, just in case, right? If you have a network issue or whatever, right? Try to submit your homework a few minutes before the deadline rather than just do it at the deadline, right? Then you never know what you might run into. But if you do have issues during the submission, contact me immediately and send me an email with your homework. Typically, I will accept that. The reason I impose a really strict deadline is I typically release homework solution right after it's due. Right? So if I have released solution and then you made a submission, then it's kind of make it a really difficult case for you to justify your late submission. Does that make sense? And I like to go over the homework solution right after it's due, when you guys have a fresh memory of what you do, right? In your homework, things for I don't give any late submission, right? For that reason, because I have once I start talking about the homework solution, how can you make a late submission after that? Okay. All right. That being said, let's look at homework 2 together. So, homework 2, problem 1 is fairly straightforward, in my opinion. It's important to know that you should not query by instance. I mentioned that a couple of times. What do I mean by query by instance? For example, I asked you to find a very simple query, right? Find the bank from Boston. The right query to write, of course, is to say you do a selection where location equal to Boston, and you do this over bank location, right? Right. So that will be the correct answer for this. Query by instance means that you look at a particular instance that's given to you, and instead of doing this, you say, okay, the bank from Boston is, I simply select, bank equal to Citizen, or bank equal to, what's the other one? Fleet. Right? If you look at these two solutions, seems that they give you the same answer with respect to this particular instance, right? However, the second answer is wrong because it's a perfect example of query by instance. That same query will no longer give you correct answers if I start changing that particular instance for the bank location schema. For example, I can insert another bank called Bank of America with location Boston. In that case, the first query is still right. The second query is no longer giving you correct answer back. Does that make sense? Okay. I can even change the location of fleet from Boston, let's say, to New York. Then, again, the second construction will give you wrong answer. So you may wonder then why I still have these instances to work with. Well, instances really is to help you understand what you're doing. So in a way, using a set of given instances, you can check at the sanity check whether a particular construction is right or wrong. But there's no guarantee if your query works for a particular instance, there's no guarantee that it will work for all instances. But if it doesn't work for a particular instance, clearly it's wrong. So it can tell you whether your query is wrong or not, but there's no way you can tell by just looking at one particular set of instances to claim that my query is 100% right. Does that make sense? Okay. So that being said, let's look at some of the interesting ones. For problem 1, I think this icon. Okay, for problem 1, okay, for problem 1, one of the interesting queries to write is which banks issue only one credit card? Which bank issue only one credit card? Several of you asked this question on Canvas and sent us emails. I actually gave a hint on Canvas. I said, you do a self-join over the issuer table. And I refer you to slides 31 and 32 from the relational algebra lecture slides. If you look at the examples over there, we talk about things like find the sailors with the smallest rating value who reserve a particular boat. Okay? It's actually the same construction, right? You do a self-join using reserve, and you make sure you're talking about the same boat, but sailor ID is different, and one sailor's rating is greater than the other sailor's rating. You purge out those ones, then do a set difference to find out the sailors with smallest rating that reserve each boat. Okay, that's the idea over there. To do this here, the idea is very similar to that. You make 2 instances of issuer. Let me enlarge this so all of you can see. You use the rename operator to get 2 instances of the issuer table. Then you do a self-join over them. Or when you do the self-join, you make sure bank are the same and card name is different. And you purge out those banks. What do you get? You get those banks who have issued more than one card. If you issue only one card, in this self-join process, you will never satisfy this condition. Bank name is the same and card name is different. If you have issued just one card. You have to issue at least 2 or more cards in order for this condition to be true. So you purge out those banks. What you get is those banks who issued more than one card. Then you use all the banks from the issuer table, subtract away those guys who have issued more than one card. You get those banks who issued just one card. A minor note is you want to use the bank from issuer to do the subtraction rather than the bank from the bank table. Can someone tell me what's the difference of the two? Yes, go ahead.
There may be banks that don't issue.
Exactly. If you use the bank from the bank location table, you may have a bank who has issued no card at all. And that will still be part of your answer, which is clearly not right. With respect to what we have asked you to do, right? Which is you have to issue at least one card. Okay? That's why we purge out the bank, the lethal banks, from the issuer table rather than from the bank location table. And the bank, yes, go ahead. Question.
Just a quick question.
Yeah.
When you're doing the projection,
You're talking about problem 4 still, right?
yeah.
Okay, go
When
ahead.
you do the projection, the second projection.
For the second projection, yes.
Yes. Do you need to specify that?
Oh, yes, you're right. I do. I do need, thanks for the correction. I do need to specify, I'm actually, on this case, no. On this case, no.
Okay.
On this case, it doesn't matter whether you put out bank from I1.bank or I2.bank. Because the condition is they're the same. So it doesn't really matter which bank value you put out. Does that make sense?
Yes, but do you need to write, or if you do this, this would work?
Oh, I see what you're saying. To be 100% semantic, right? Yes, you have to specify I1 or I2, but it doesn't matter which one you put out.
Thank you.
Yeah. But in the speaking of which, that's actually an excellent question. Speaking of which, if you look at the example from the lecture slides talking about the sailor with the smallest rating who reserve a particular boat, in that case, you do have to be a little bit careful which one you put out. You want to put out those with a larger rating in the comparison, so that the one with smaller rating has never been put out. But in this particular case, it doesn't matter whether you put out the value of bank from I1 or I2 because you have a condition I1.bank equal to I2.bank. Okay. Now let's move on to problem 2. So problem 2, I think the interesting ones are maybe, are 4, 5, maybe 8 as well. The others are, in my opinion, fairly straightforward. Okay, fairly straightforward. Let's look at 4 together. Problem 4 says, for each shop, find products served at this shop that are liked by none of the customers who visited that shop. So a lot of you, some of you at least, approached me and said, oh, I have trouble in expressing this for each shop semantic. I don't know how to do for loop in relational algebra. I know how to do this for a particular shop, but I don't know how to generate that for all the shops and for each shop. Right? The response to that is don't be tricked by this sentence for each shop. Right? Let me ask you a very simple question. Right? Suppose given this set of schemas, let me ask you guys, how do I find for each shop the products offered by that shop? How do you do that? For each shop, find the product offered by that shop or served by that shop.
You just project out the products
For a given shop?
for the table.
But that will work for a particular shop, right? But I want you to do for all the shops, for each shop.
So when you do just serves, you just keep S name and P name from serves.
Yeah.
And that gives you all.
Yeah. You just put out S name and P name from serves. That's for each shop. Right? So think about it. So the first response I got, I suppose what you mean is you put that out, you know, the product name, but you do this shop name equal to a particular value, let's say X. And you do this for serve, and you say somehow I need to do this for each X, right? For each shop you do this. But there's no for each, there's no for loop in relational algebra, so this will not work. But if you think about it, it's actually quite straightforward. For each basically means you put out all of them. So instead of doing this, you simply say put out the shop name, the product name, on serve. You're done. And this will show you for each shop the products served at that shop. So don't be tricked by for each. For each simply means you want to return a set of combinations of shop's name and product name. That's all it means. That's all it means. Question on this so far? Good? Now, that being said, let's look at how we do this, right? For each shop, find products served at this shop that are liked by none of the customers who visit that shop. If you have trouble in figuring out what the solution should be for a particular query, right? The first thing you do is to figure out what is the schema of the output supposed to be. What the output, the schema, should look like. In this case, since you asked me for each shop, find the product, blah, 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 whatever, I don't care. There's some condition to qualify those products. Right? That's the sentence. Serve at this shop that are liked by none of the customer who visit that shop. Those are what we call conditions to qualify what product to put out. I can supply actually any condition I want. In this case, I have a particular condition you need to work for, right? But regardless of what condition is being specified, you know the output should be a shop name and product name, and a pair of these values. Does that make sense? It's just for different shop, the condition to qualify that product will be different. That being said, the first thing to know is that the schema of the output, must be shop name and product name. Okay? Then you look at your input schemas input set of schema, you look at where do I get this guy? Well, you notice that it's from the serves. If I put that out as name product name from the serve table, what I get? I get all products being served at each shop. What can you say about this with respect to your final answer? Well, you can clearly there's a relationship, which is if I use this to represent the output of this, meaning all the pairs of shop name and product name, my final answer must be a subset of this. Because this shows all products being served at every shop. My final answer clearly is a subset of that. For each shop, I get rid of some products. I keep some products at that shop. But there's nothing more to add than this. You cannot add a product that's not served at a particular shop to the final answer. That's clearly not the case, right? So the final answer must be a subset of this, meaning that this will be my answer. Okay? So this actually is the key to figure out the solution to this problem. Okay, in order to find this, one way is to somehow find this directly. Another choice, once you have this view, is to figure out this part. Right? And you simply use this, subtract away those in that part, in the red shape, in the red region. Does that make sense? Now let's look at what is in the red region. Okay, each element here in the red region is a shop name and product name. For a particular shop, I serve this particular product, and this product is liked by at least one customer who has visited this shop. If that's the case, you must be in the red region. Otherwise, you must be in the answer set. Because otherwise, it means that I'm serving this product. It's not liked by any of the customers who have visited me. That's exactly what the answer is looking for. All of you follow this? Yes? By the way, when I go over this, I do ask you to pay attention, right? Because I don't want you to come back later on and ask me the same question. That only shows me you didn't pay attention when I was going over this. Okay? So I'm going to do a test. Right after I go over this, I will ask one of you to give me the solution and explain to me the solution. If you cannot do that, I mean, I don't know what's the point of coming to lecture, seriously. Okay? If I were you, I would better just watch YouTube, the highlight of Super Bowl game. Better. Or, even better, have you focus? Have you looked at what they had done yesterday? Yeah. The landing of it. Both of them land simultaneously. In order to do that, it takes imagination, takes creativity, but above all, it takes hard work. Okay? If you guys cannot even do this, there's no way you can do habit focus. I can tell you that. Okay? So let's come back to this, okay? So any dot here is a pair showing that a shop serves this product, and this product is liked by. So what does this mean? This means right? Obviously, because that's the entire green set means to begin with. Secondly, P is liked by some customer. Some customer means greater than 1, greater than or equal to 1. Visited that shop S. So the key point is how do you figure out this part? This, for a given shop, the product liked by one of the customer visited our shop. At this point, I think it should become really straightforward, right? That's simply a natural join between what? Serves, join with, go ahead, thanks. Join with liked and You also need to join with visit. Okay, let's do this. Let's look at what happened here. Served is shop name, product name, and there's the price. Price is irrelevant in this discussion, so we can safely ignore that. Likes is customer and product, and visit is customer and shop. So this is customer and product. This is customer and shop. This is shop and product. So this natural join happened on product, and this natural join happened on customer. Then finally, there's natural join happened on shop as well, which basically give you shop server product, the product liked by a customer, and customer has visited the same shop. And you simply put that out. To make them union compatible, you put that out the shop name and customer name. Shop name and product name. At this point, you don't care which particular customer has liked that product. So you put that away customer information. You don't care about price information either. You're done. So all of you follow this. Go ahead.
Do you really need the served natural join?
Do you really need a served natural join? You do, because if you don't have this, how can you be sure that the product is served at a particular shop?
Well, even if you subtract it from the...
You like a product, you visit the shop, but it doesn't necessarily mean that product is served at that shop. Okay?
Yeah, but even if you subtract it from the served set, it wouldn't be there.
I see what you're saying. Yes, good observation. You don't necessarily need served for that. Yes. So you subtract something more that's not even here to begin with, so it's fine. Meaning that you looking at this graph, if you don't have the served table, what happens? You get something like this plus something here. And you use the grid to subtract this and this, you still get, sorry, this is the final. You get, if you don't have the served table in the natural join, you get this red part plus something outside this green circle. Then you use the green circle subtract of this and this, you still get this back. Yes. Okay? Very good observation. Question for this before I move on? I will tell you one thing, right? For the midterm test, all problems, I promise you, all problems in midterm test will be similar type of questions from your homework. But of course, it cannot be the same problem, right? Otherwise, what's the point of the test, right? So it will be similar type of problems. So it's really important for you to understand how we constructed the solutions for your homework problems so that you can apply similar constructions to that similar problems you will encounter in midterm. And after the midterm, it's up to you. Either you can throw away everything we said, which is fine, or you remember it and make some use of it in your future work or career development. That's up to you. But before midterm, you have to care. After midterm, whether you care or not, I don't care. But before midterm, I make sure you have to care. Okay, go ahead.
Do you have a good resource for practicing more of these kinds of problems? It's not quite sticking for me, unfortunately.
Yeah, so one, I give you two pieces of advice. One is make sure you go back to these problems after I go over the solutions. Without looking at the solution, try to solve them again.
Okay.
If you can do that, that provides ample exercise already, in my opinion. You can solve all of this. That's more than enough. You don't need any more exercise.
Okay.
That's advice number one. Advice number two, I will release some additional quiz problems. That's another value of practice. And a third value is look at the problem at the back of your textbook. You can try to solve those.
Okay.
And the textbook actually comes with solution to all the odd number of questions. But really, in my opinion, if you can just work yourself out of all these problems in the homeworks without looking at solutions, you don't need any more exercise.
Okay.
More than enough. Okay? Number 5, find all customers who visit only those shops that serve some product they like. Okay, how would you do this? So first of all, take a good look at the problem. Now let's look at the solution, right? Find all customers who visit only those shops that serve some product they like. What this question is asking is the following, right? I don't want to find those customers who has visited at least one shop. Who has visited at least one shop that serve no products he or she likes. That make sense? I don't want to look at those customers. I want to look at those quote-unquote smart customers where they plan their visit ahead of time. So they know that shop, I only visit a shop if there's something I like. Otherwise, I don't want to go there to spend time in that shop. That make sense? That's what this query is doing, right? So how would you do this? So the basic idea is, first of all, you do a natural join between like and serve. You figure out the customer and shop name. What does it give you? Can someone tell me this? The natural join between like and serve, you figure out customer name and shop name. What does it give you?
Gives you customers that visit the shops that serve what they like.
No, there's no visit here, right? Look at it.
That did it serves them.
Yeah, just products they like. So did you?
Can you be a little bit more precise? Let somebody else help you to.
Okay. It should give you customers
Yeah.
that have gone to shops that serve something they like.
Okay. Almost right, but remove the part you say has gone to the shop. If they have,
Right.
No,
they
no.
may have gone, they may not have gone to the shop. So it gives you the possible combinations between customer and shop name such that this shop serves some product they like. But whether those customers have visited that shop, I don't know. They may have not. But at least it gave me the combinations of customer name and shop name such that this shop serves at least one product this customer likes. It gave me all such combinations. Does that make sense? Now, what do you do from here? Well, you take visits, print out customer name and shop name, subtract away from that, what do you get?
Customers that don't visit the shops that sell the stuff they like.
Yeah. Actually, to be precise, because if you say customer don't visit shop, serve anything they like, that means that implies you have never visited even a single shop serve some product you like.
Oh.
That's not the case. What's happening here is you have visited at least one shop that serve no product you like. These are two different things. Customer do not visit shops serve product they like, and customer visited one shop that serve no product they like. These are two different things. You have to be a little bit careful in how you phrase what you're looking for. Does that make sense? What this gives you is customer visited at least one shop, at least one, that serve no product he or she likes. Because otherwise, you should not be subtracted away from this subtraction. If you visit a shop that serves some product you like, that will be in the second part and being subtracted away. Does that make sense? Or to be precise, to help you fully understand what's going on here, is two circles. One circle says, this is serve for the customer name and shop name. What this tells you, any dot here tells you, so this dot means this is customer C1 and shop 1. What that means is customer 1 visited shop 1. It simply means that, nothing else. Does that make sense? Now I draw another circle. Again, this is the same schema, but it's serve, like to draw with like. And this is customer and product. This is product and shop. So nothing gonna happen on this. But I put out shop name and customer name. What do I got? So maybe I should have used red color here. Right? So this gives you the red circle. What does it give you? We just talk about this, right? Any dot here implies customer 2 likes at least one product served at shop S2. Does that make sense? Yes or no? And if I do a subtraction of the two, what do I get? I got this part, but not this part, not the purple part. What is the purple part? Purple part means you visited the shop and the shop served at least one product you like. What is the remaining part of the green circle? You visited the shop and the shop served no product you like. Are we done yet? We're not done yet because there's a keyword only. If without this keyword, we're done. We're finding customer who visited some shop, served no product they like. We're fine. That's exactly the answer. This is exactly the answer. Do all of you follow this? But there's a keyword only. These are really strange set of customers you're looking for. Right? Meaning that they spend time visiting shops, but they only go to the shop with no product they like. You wonder why I want to find such customers. Well, if you're Amazon or Google or some big offline retailer stores, you are interested in those customers. You want to find out why they're doing this so that you can maybe change your marketing strategy. Why? At the end of the day, you want to make more money, don't you? Right, so this query I asked you guys to do is very practical. Right? Big retailers store, Amazon.com, they always do things like this. For example, Google may be interested. I want to find those customers, those net servers, who only visit the website they don't like. Right? That's strange, yes, but I want to find out those strange users and see what's going on with them, right? Question over there?
Yeah, I guess I don't understand how you're getting who visited what shop out of the serves.
Oh, you simply do a projection of the shop name and customer name. Oh, sorry, from the visits. This should be the visits, not the serve.
Oh, okay.
Yeah, I made a mistake over here. Sorry. Thanks for the correction. Okay. Now, how do I get those only visited shops serve, product they don't like? We get, so let me recap, right? What we find so far is customers who visited at least one shop or some shops that serve no product they like. But the problem is, those customers, I will draw another circle, okay? The other circle, I'm gonna use, okay, let me use purple color for this. This will be customers visited some shops that sell product they like. Does that make sense? Now if I do another subtraction, I will get those who visited only, because if you think about these guys here, this part, this customer visited some shop, serve no product they like. They also visited some shop that serve product they do like. If I use this whole thing subtract with these guys, this part in the middle is really what I'm looking for. Because only those shops serve product they don't like. You follow this? Yeah? That's why there's another subtraction over here. But actually, all I need to do is put out customer name. From here, this is a set of customers who visited some shop, serve no product they like. Do all of you follow the rationale? Same? Here. Go ahead.
Sorry, can you say one more time if this was on the right? This is supposed to be the right one? Or, so, like,
Yeah.
I got a hard time understanding the difference between the circle on the far left and the far right.
Okay. So look at, we have explained so far, right? All of you follow this so far? So what I got is customer and shop name. The customer visited that shop, and the shop served no product they like. And at this point, I put out all customer names from that. I don't care about shop anymore, because as long as you have visited at least one shop that serves no product you like, you qualify as a potential candidate. I don't really care which particular shop make you to be a candidate of my answer. At this point, I don't care. That's why I put out the customer name from that. So far, so good? So the question asks you to find those customers who visited only those shops serve the product they like. So if I do a projection over the visits, what I got? I got customer visited. So I think I might have a mistake in this answer here. Let me think about this. I got customer visited some shops. Subtract away this. You visited. Oh, I see. I got. So I made a mistake in solution to 6 and 5. So I flipped the order. Let's look at this. If I flip the order of the second and do the subtraction like that, I got customer who visited some shop served at least one product they like. Does that make sense? Meaning, think about this part. I use the red, subtract away the green. What do I get? Meaning, instead of this, subtract away this, I use this, subtract away this. What do I get? I got customer visited at least one shop, serve at least one product he or she likes. Does that make sense? Do all of you follow this? Simply flip the order of the two. Then you use customer who visited some shops minus away this. What do you get? You got customer who visits only those shops serve no product they like. Okay? Now coming back to 5, what if I go back to this part, which is customer visited at least one shop serve no product they like, and use the entire visit, all the customers who visit some shop, subtract away that, what do I get? Let me pose this question to you guys. What do I get? Go ahead.
Customers who haven't done that. So customers who haven't visited the shop. It doesn't happen.
Yes. Customer, can you repeat so the rest of the class can hear you?
Yeah. It would be the customers that haven't visited the shop that don't serve at least something that wants.
So in other words, customer has never, those customers who have never visited any shop serve no product they like. In other words, the customer who visit only those shops serve at least some product they like. So that's the difference between the solution for 5 and 6. Do all of you follow this? A simple flip in the order when you do subtraction, you get totally different results. But really to understand that is to think about these two circles here. If you use the green to subtract this, you get this part, which tells you customer visited at least some shops serve no product they like. If you use red minus green, you get this part, which is customer visited at least one shop serve some product they like. Then you use visit to subtract either one of them, you get your answer. That's kind of the trick for 5 and 6. Okay? Now, some of you asked also a question regarding, let's say, 10. Okay, let's look at 8 actually together. find those customers who visit all and only those shops Alice has visited. This actually built on the solution of 7. 7 says, find those customers who visit all shops Alice has visited. Can someone tell me how to do that? Was number 7. How do you do that? Go ahead.
You project out the shop names from the visited where the name is equal to Alice, the customer name, and then you divide the
divide by visit.
Sorry, I don't have like the name, so I can't.
Divide by the visit.
Visit, yeah.
Yeah. So it's really a straightforward application of division.
Right.
Of course, you have to be a little bit careful who divided by what. You use all the combination of customer visited shops divided by the list of shop names visited by Alice. But it's a really straightforward application of division. That being said, what do you get? You get customers who have visited all shops Alice has visited, and more. They have visited all those shops visited by Alice, but they may have visited some more shops. Right? Let me give you an example of that. So let's say I have my schema looks like. So this is my visit schema. I don't care about the number of times, so I'm gonna only show customer name and shop name. And let's say I have Alice, shop 1, Alice, shop 2, and Alice, shop 3. So the first step is you find S1, S2, S3. Then you use the remaining part from here and divide by that. You got those who have visited all the shops visited by Alice. All of you follow this? Now let me materialize this green part. Let me give you some concrete example. Let's say Bob visited S1, S2, S3. But Bob may also have visited S4. So I visited all shops by Alice and more. I may have another guy called, let's say, Tom, visited only S1. So my answer to this will be simply Bob. Right? Visited all the shops by Alice. But what's the difference between 7 and 8? 8, in addition to that, asks you to find those customers who have visited only those shops by Alice. So first of all, you have to visit all the shops by Alice. Secondly, only those set of shops. So Bob will be disqualified because of that. Because you have visited, in addition to S1, 2, 3, you have visited one more shop or 2 more. I don't really care. Right? Do all of you follow this so far? So how would you do this? The idea, of course, the first part is the same. You use the division to find. You use the division to find those visited at least all the shops by Alice. Then all you need to do, if you think about it, again, you use the set semantics, right? You use the set to represent this. What you got is, so what do you got here? You got customer who visited all shops visited by Alice. And you want to subtract away those customer who visited at least one shop not visited by Alice. Does that make sense? You find those customers who visited at least one shop not visited by Alice. Then you subtract away the green from the red. You got this part, but not this part. What do you got? Who visited all the shops by Alice and visited none of the shops not visited by Alice. you visit only those shop by Alice. Does that make sense? Do all of you follow this? Yeah.
In the equation, you have a cross product.
Oh, you're talking about this particular solution, right?
Yeah.
Okay, let's pause that. Because I haven't started talking about that. I'm asking whether all of you at least understand what these two circles are and why we're doing a subtraction of the two. That you are okay with, right? Go ahead.
So Alex would be in the answer, right? Alex would be one of the customers that they
Yes,
all
very good catch.
Okay.
So technically, I can include Alice as one of the answers because she definitely visited only those shops visited by herself, right? So this is one of those corner cases. What should you include Alice herself or not? It doesn't really matter in this case either way. Okay. That being said, let's question over there.
Could you explain the circles one more time, please?
Sure, definitely. First of all, do you understand the green circle?
It's
green circle represents all the customers who visit all shops visited by Alice. That's just a division. The red is those customers who visited at least one shop that has not visited by Alice. In other words, you visit something that Alice has not been to. If you subtract away the green from the red, what do you get? You get those who visit all the shops by Alice and has not visited any shop not visited by Alice. So you get those only, right? So that's kind of the logic here. So our job is reduced to this. How do I get the red circle? Well, the idea is you put out all the shop names that ever visited by Alice from visits. And you join with cross product, not join, cross product with customer. What do you get? You get all possible combinations of customer and a shop that's visited by Alice. All such combinations. Whether the customer has visited that shop, I don't know, but I show all the potential combinations. Customer and shop combination between any customer and any shop visited by Alice. That's what I got from this cross product. All of you follow this? Question over there?
You did a cross product first, or you use subtraction?
Say again?
I didn't hear that right. You use the cross
I haven't reached that subtraction yet. I'm just talking about this. Okay? Do you get this part at least? The customer, any customer, combined with any one of the shops visited by Alice. That's what I got from this cross product. That should be quite straightforward, right? I think from the construction of this. Go ahead.
So could this be replaced with a conditional join?
It's not. It's just a simple cross product. It's not a cross product. Is not. Well, you can kind of think cross product as a special condition join where there's no condition whatsoever.
But in this case, you already have.
That's just a selection. That's before I do the cross product.
Okay.
Do all of you follow this? Now what do? I use with this subtract with it. First of all, if I use with this to subtract away this, what do I get? I get, what do I get? Okay.
You get basically anyone who's visited a shop not visited by Alice.
Yeah, exactly. Exactly. Let me repeat what it said. You got a customer who visited the shop that's not visited by Alice. Because otherwise, if you visit the shop that's visited by Alice, when you do this subtraction, you will be subtract away. Because it must be that customer name and shop name combination must be in the second instance in this subtraction. What's over there?
Doesn't visits and then the other thing have to be unity compatible in order to do that?
Yeah, I actually call that. Well, you need to project away the number of visits, meaning that you do a projection of customer name and shop name. Okay. Because to his question, right, the schema of visits is customer name, shop name, and number of visits. So they're actually not unique compatible. So that's just a simple projection. You add here customer name and shop name before you do subtraction. That's a simple fix. I will fix this after this slide. Any question on this? Now I project out those customers. What do I get? I got exactly my red circle. I got exactly my red circle. Then I'm done. Okay? Any question on this? Very good. Okay.
I'm just wondering if you could give us a list of the order of operations and set operations.
Say again? You got it?
Could you give us a list of the order of operations and set operations? Could you give us a satellite selection always goes before protection? But I just realized
Selection always goes before protection. No. The ordering of relational algebras can be arbitrary. You can combine them in any way you like. It depends on what you want to do, right? Now in this case, the idea you do selection first is you find those records concerning Alice. Then you product the shop name. If you do the production first, what do you get? You get simply a list of shop names.
but the cross product in this case, even though the line goes before the subtraction.
Well, I think I understand what you're trying to get, which is if there is some sort of general rule I can follow, right? No, unfortunately no. Each case is different. You have to think about how you construct each query with regard to the query itself. Does that make sense? But think about this. The reason why we do the parse stuff like this is to find out, but every single query is built in an incremental fashion, right? Let's revisit this query we just talked about. What we have done is essentially, first of all, I find the shops visited by Alice. Then I cross-product with customers. That gives me all the possible combinations between customer and the shop visited by Alice. Now you visit software with this. That shows me a customer visited the shop that's not visited by Alice. Because otherwise you must have been somewhere away. That's it. That's kind of the way my logic is. Question over there?
I think what he's asking about is just general order of operations.
General order of operations.
Visits minus customers and then crossing.
Oh, I see what you're saying. So if you want to be explicit, the ordering of the operators, you can add cross this bracket, anywhere you think that might have a computer. Right? But in this particular case, you don't have to do that because subtraction only happens when you have unit-compatible instances. So it's impossible for you to do Windows subtract with this, then do cross-product, because they are not even unit-compatible. Does that make sense? Yes? But if you want to be sure, you can always add bracket to indicate ordering of those operators. All right? The last one I think worth a little bit discussion is number 9, which is for each product, find the shop that serves at the lowest price. But this particular query is identical to the one you have seen from the slide, which is the sellers reserve a boat with a smaller rating. Right? It's identical to that. That being said, all you need to do is a natural join, a self join between the serves, between two instances of the serve table, and you make sure the shop name is different, product name is the same, meaning that the same product is served at two different shops, and one has a higher price than the other one, and you put that out, that combination of shop and product name with a higher price. In this process, the one that served that product at the lowest price will never be put out. Then you subtract away these guys, you get for each product, the shop served that product at the lowest price. That's what you get. Okay? The last one is a simple division, so I will skip that. So that being said, I'm going to stop here and take a minute to kind of give you some general overview of relational algebra and SQL, right? If you look at these queries, they sound like really simple, straightforward queries. But this is essentially, if you work for marketing firms, if you work for Google, if you work for Facebook, these are things you do on a daily basis, right? Who has visited all the page, who has liked all the page that Alice has liked, right? I'm sure Facebook are doing such kind of analysis on a daily basis. Why? Well, I don't know. Maybe those are the ones you want to recommend to Alice as for friends. I don't know whether you have ever wondered how Facebook recommends some friends to you or Google recommends some pages to you. Well, they track the patterns of you when you use their service and look for the other users who share similar patterns in making their recommendations. the type of queries we have done here are exactly those type of analytics they do. Does that make sense? So these are driven by real world examples. It's not like I just make up some examples to challenge like a green teaser problem that challenge you. No, it's not. Right? It's real world examples. That means that relational algebra and SQL goes hand in hand. Right? If you have a difficult time in solving this query in relational algebra later on, of course, you will have similar challenges in trying to express this using SQL. So it's really important for you to get a really good understanding of how to do this in relational algebra. Then later on, you will be able to transfer the same thing to SQL. That means that the rule is to apply and construct your queries incrementally. If you think about all the things we have done, we start with one particular set. That's not necessarily your answer, but how contribute towards the construction of your final answer. So the key word is construct your answer incrementally, one at a time, one set at a time. One set at a time. Okay? And take a modular approach. By modular approach, for example, this is a modular approach, right? I find those who have visited all the shops Alex has visited. Yeah, I find all those who have visited some shop Alex has not visited. These are two modules of my final answer. There, I just do a subtraction between the two. Right? So that's always the rule you want to apply. Okay? Okay, now let's look at problem number 3. Problem number 3 asks you to demonstrate the understanding of the concept of keys and superkeys. But before I dive into the detail of this, let me give you a quick review of the concept of key and superkey. Right? So I will draw a set diagram here. So let's this set represent all the superkey for a schema. Okay? All the superkeys for a schema. There could be many of them. By the way, every schema has at least one superkey, which is all the attributes in the schema. Because the relational instance must be duplicate-free. If you use all the combinations of all attributes, that indicates no two records can have same values on all those attributes. Naturally, that's a superkey. So every schema has at least one superkey, right? Which is the schema itself, all the attributes in the schema. Do all of you follow this? Now, keys are special kind of superkeys, meaning that basically means they are a subset of your superkey. They are a subset of superkey such that any element from the set of keys, what's the requirement? Can someone tell me what's the requirement in order for something to be a key? Yeah.
None of the subsets can be superkeys.
Yeah. None of the subset of attributes in X belong to the set of superkeys. Right? That's essentially what we're working. In other words, if you view X as having one or multiple attributes, by the way, if X has only a single attribute, you're done. It must be a key. Because the only subset of that is empty set. But let's say X has multiple attributes, M of them. The point is, if you remove any one of them, the remainder of them is no longer in this set of superkeys. That will make X itself a key. All of you follow this? Example, student ID and student name. Obviously, that's a super key because no two records can have same student ID values. You can have duplicate values for name, but you cannot have duplicate values for student ID. So this combination is unique. For any record you can think of a student table. But if I remove student name, student ID is still a super key because no two records can have same values on the student ID column. So I find a subset of this, which is a super key. So itself, cannot be a key. It's not a key. But it's a super key. Okay, so that's the basic concept between super key and keys. And you may have multiple keys. For example, for student, I have student ID, that's a key. I also have login and another key. In that case, I choose one of them from here as my primary key. And the other one automatically becomes what? Candidate keys. Excellent. Automatically become your candidate keys. Now finally, where is the concept of foreign key? Well, when in the process of constructing a table, if you ever take a key attribute, whether it's a primary key or candidate key, from another table, then in the second table, that key becomes a foreign key. Okay, so that's a quick review of the concept. That being said, let's look at this problem. Consider the following specification is absolute. So the way you solve this problem is to look at first of all, what kind of relationship is captured by this specification, right? This is a very simple specification, like you've heard that like your homework one, but it's much simplified version of that. So you have an absolute, so which means you must have an absolute entity set, and you have a club, you have set of clubs, so you must have a club entity set. And there is some sort of relationship between the two, right? Which is absolute is a member of a club, right? Like an NFL player is a player for a particular NFL club, right? However, there are constraints, right? The constraint is every single athlete must be a member of some club, meaning that you cannot have an athlete floating around without being a member of any club. That simply indicates there's a total participation constraint here. Does that make sense? Yes? And it goes on with additional constraint which says each athlete can be a member of at most one club, but a club may have multiple athletes. So if you draw this set diagram, what do you get? Well, each athlete, you cannot, if that's the case, you cannot have a second line like that. You can be a member of at most one club. However, a club may have multiple athletes in it. And you cannot have an athlete floating around without being a member of any club, so this guy must be connected to some club. But it says nothing about whether a club must have an athlete in it. So it's okay for me to have a club who has no athlete in that club. Does that make sense? All of you follow this? The question is, how do you translate this to this ER diagram here? Someone help me with? Go ahead.
With the arrow on the athlete side?
Yes. One to many. The arrow coming out of the many side and goes towards the relationship side. That indicates a one-to-many mapping between the two. One club with many athletes, each athlete goes to just one club. So one to many. Was it good? Now, the way you solve this problem is first to construct this ER diagram. Then from this ER diagram, you convert this to relational models. How would you convert this to relational model? Well, obviously, there must be an athlete table with AID, name. What else do we care about athletes? Login ID, right? And the club must have a club ID, address, and title. Right? That's my initial design. Obviously, AID is the key, CID is the key. Are we done yet? We're not done yet, right? Because we need to somehow capture this one-to-many mapping. If it's a many-to-many mapping, we said it goes to a. If it's a many-to-many relationship, it goes to a table itself. If it's a one-to-many, fundamentally, this is a review of what we have said before, right? Fundamentally, you need to have some sort of representation to capture these lines. These lines represent those relationships. And the way you represent them must be able to uniquely identify every single line from this set of lines. Right? So how do you uniquely identify this set of lines? Go ahead.
Add the club ID to everything.
Excellent. You add club ID to the ASLET table. Why that works is, if you think about it, this is club ID 1, club ID 2. If I just add to the ASLET who are a member of that club, what do I get? For this ASLET, I get an additional attribute club 1. For this ASLET, I get another attribute called club ID 2. Club ID 1 as well. Not only I can identify this ASLET, but because each ASLET is connected using only one line, by adding this club ID, I can uniquely identify the line. The important observation is you have at most one line for each ASLET. If you have more than one line, this will not work, because adding one club will not be able to, one club ID will not be uniquely identify that line. Because, but in this case, since you only have one line, adding that club ID will work. Will uniquely identify that line. Question?
In this case, CID is your foreign key, right?
Yes,
To that.
exactly. CID become a foreign key.
I wanted to ask if for a foreign key in the athlete table, can you use the title as well since it's unique?
Excellent. So title, as we said, is unique. So this is the candidate key. So the question is, can we, instead of put CID here, can I put title here, club title here? The answer is yes, you can do that. Because the whole point is to uniquely identify the line. I don't care whether you use club ID or title, as long as you can uniquely identify the line associated with the ASLET, then you're fine. So you can use either the primary key or a candidate key.
So then your primary key in the club table can also be title.
Yes, but you don't have to make title as the primary key in order to use that as the foreign key.
Oh, okay. I see.
Meaning that a candidate key can't be used as a foreign key.
All right.
Okay, so let's go back to the basic design. Let's say we use the. Yes, question?
Results, whatever it is, they ask to go with the CID.
Yes, so that's what that's what I'm gonna go next to. So a club make an ASLET in the same club must be assigned with distinct rating. So we haven't captured this yet. Right? Which means for each relationship, club and ASLET, there's a rating value attached to this relationship. Club assign a value for the ASLET's rating. So when you take over the club ID, you should also capture that value here as part of your ASLET table. Does that make sense? Now, how do we capture the fact that each club must have a distinct rating for every ASLET in that club? How do we capture that?
Make CID and rating a key.
Yes. So CID, first of all, is a foreign key. And the combination of this is another key, meaning that you got another candidate key. Can you justify why this is a key?
Because you can't have two athletes in the same club that have the same rating.
Meaning that, in other words, if I look at CID and rating, I look at these two values, can I have something like club ID is 8, rating is 10, I have another value like that in the ASLET table. Of course, ASLET, this is 101, 102, their name, and other things. Can I have a combination like this? Yes or no? Obviously no, because the spec just said ASLET in the same club must not have different ratings. Does that make sense? This makes it a super key. How do you argue that this is a key? Well, it's perfectly okay to have two ASLET with the same club ID. So club ID itself is not a super key. It's also okay to have another club with another ASLET with the same rating. So you may have duplicate on reading as well. So none of the subset of this is a super key. Hence, the combination of club ID and reading is not only a super key, but also a key. But since you already choose ASLEE ID as a key, this combination now become a candidate key. Of course, you also have login as a candidate key. That's trivial, right? That's trivial there. All right, so that's the answer for this problem. Any questions? Go ahead.
Can we clarify this? Because it seems like you said in the past that properties of a relationship can't be a key.
Say again?
That properties, attributes of a relationship can't be a key.
Well, what I said is relationship set has no keys. That's what I said.
So an attribute of a
Meaning
relationship.
that when you are designing this, there is a reading here, right? You cannot make any attribute of a relation set as a key. Relation set doesn't have key to begin with. Okay.
Could login for sorry. Yeah, could login for an athlete be a candidate key?
Yes, of course. That's another. But that's trivial, right? Compared to this one, right? So that's clearly indicated by the spec.
So when the athlete table absorbs the attributes of the relation, that
can be.
A single attribute can be a key in the athlete table.
What do you mean by single?
So if the relation had multiple attributes, then a single one of those attributes could be a key in the athlete table.
No, I mean, it really depends on the spec. Let me change the spec a little bit to demonstrate it. Let's say, I don't say athletes in the same club must have different ratings. I say all athletes must have different ratings. How does that change the discussion here? Can someone help me with? Go ahead.
Then the rating would be a candidate key.
Then rating itself will be a candidate key. Each club assigns a rating for its athlete, but all clubs work together in this assignment, and all athletes, no matter which club you work for, must be having different ratings. In that case, rating becomes a key itself. So it really depends on the spec.
So if that was your spec, would the rating become an attribute? Like just in the ER, we're just talking about ER, would rating become?
Will rating be an attribute of athlete or rating be an attribute of this relationship set? If the spec says club assign rating to athlete, you should still make rating an attribute of this relationship set to indicate that athlete by him or herself do not have ratings. It's really because they participated in this interaction they got that rating. Does that make sense?
Right.
Okay. All right. I think I spent a whole lecture to go over homework 2, but I think this is really important for you to catch up. I noticed, first of all, a lot of you are not here. For those of you who are watching the streaming live or you're going to watch the YouTube video offline, you want to make sure you capture this, right? I don't want to repeat myself down the road. So if you ask any question on homework 2, I will simply refer to this YouTube lecture. Okay. Secondly, for those of you who are here, I do notice a fraction of you didn't pay attention. Okay, so towards the end of it, I'm going to ask one of you to solve one of the problems I just mentioned. No, I'm kidding. I don't want to impress you, so don't be nervous. But next time I will. This I work with. Now, I do have a few minutes left. Instead of moving on, let me kind of give you a preview of what's coming next, okay? I'm not going to release homework 3 today. Rather, I will ask you to focus on your phase 1. Use this time to focus on phase 1. At the time when phase 1 is due, 2 things are going to happen. 2 things are going to happen, right? One is homework 3 will be released. Okay? Secondly, phase 2 will start. And in order for you to work on your phase 2, what I have done, let me show you. Oh, actually, I have a. Okay. First of all, I have set up a bunch of databases on the database server. So now you see we have 80 databases being set up. Okay? Each of these databases has a unique username to access that, and that username has full access control over that database, meaning you can create table, add tuples, and so on and so forth. And you will use this to work on your phase 2. And you will contact the TAs to get the password for one of these databases. Okay, a username and password. And that same username and password, by the way, will allow you to SSH to that Georgia server. These are actually 2 separate user accounts, but to simplify, your job, I make 2 username and password are the same. Meaning there's one username to access the Unix server, then another username to access the database server. I purposely make them the same username and same password, but they're still logically 2 separate accounts. Does that make sense? Let me finish that. Take your question. Once you are in phase 2, what you would do is something like this. Let me show you quickly what I got. So I will provide a sample code to you. You see, this will basically, it's a very simple Java code. When you execute this Java code, it connects to the database. It asks you to type a bunch of queries. You can type a simple query by yourself. And you get results from the database. You can type another ones like, and you get the result from database. Okay? So you want to, of course, you want to build based on this by extending it with more functionality. But this actually, if you think about this, this is a simple MySQL client program already. And I tell you, the number of lines of code to do this is less than 100 lines for the one I just did. To connect to the database, execute an actual query, get the results back, and display it to the users. So what you will do in your phase 2, which starts right after your phase 1 is submitted, is that I will release the sample code I have developed here, and then you will basically take that sample code and expand it with more functionalities. That's essentially what happened in your phase 2. Okay, now there's a question over there. You want to take it offline? You want to ask in front of the
I was just wondering how the database is associated with like the teams that we're in.
So 2 of you will share one database and one user account. Does that make sense? All right, with that being said, I'll see you next week.